Alright, so redox reactions are not as easy as the others, but this is the other class that you'll need to be able to recognize. So redox reactions, we've got reduction and oxidation occurring within these reactions. So remember our mnemonic. Leo the lion says grr. This is probably the most helpful mnemonic that I know in chemistry. And it's very easy to remember. And once you've written Leo, you can remember that this stands for lose electrons, you become oxidized. And if you gain electrons, you become reduced. So these are the key elements to oxidation and reduction. So if you've got an agent that loses electrons, these have to happen together. If it loses electrons, it's got to give those electrons to something else. So it's got to give them to something else that's gaining electrons. So if something is oxidized, it is a reducing agent because it's going to reduce something else. So reducing agents get oxidized in the process. On the other hand, if something is gaining electrons and becoming reduced, it's oxidizing something else because it's taking those electrons from somewhere else. So we could say that this guy is an oxidizing agent. So the oxidizing agent gets reduced itself because it's taking electrons and oxidizing something else. The oxidized component is the reducing agent because it's losing electrons and it's giving those to something else that gets reduced. Okay, so now how do we recognize these? So to recognize when we've got redox reactions occurring, it's useful to figure out the oxidation number of our substances. So oxidation numbers are assigned charges to covalent compounds. So you can kind of think of these as like pseudo charges. So we assign pseudo charges, and I say pseudo because covalent compounds aren't really charged, right? They're sharing electrons. They can have partial charges on them, and sometimes they're very nonpolar, in fact, and don't have any charges on them. They share equally. But we can still assign these pseudo charges to our compounds. So we assign pseudo charges to our covalent compounds to see if they change, to see if they gain or lose electrons during the reaction. And this is so that we can observe the change in the electron number during a reaction. So before we actually look at reactions, let's look at how we assign oxidation numbers. So typically when I'm assigning oxidation numbers, I say that the more electronegative atom is going to get its preferred oxidation state, is going to get its preferred charge state. Okay, so these are some good examples. So this is kind of rule number one. Rule number two is that hydrogen is always +1 when you're evaluating its oxidation state, or it's 99% +1. It could possibly be -1, but that's going to be very, very rare. So we don't really have to worry about that. When you see hydrogen, think it's +1. So let's look at what is this compound called? Hopefully you said dinitrogen pentoxide. So there's 5 oxygens, 2 nitrogens. So oxygen is going to get its preferred negative state of -2. So again, we can just draw our charge box like we do for ionic compounds. So we're going to do charge, we're going to look at number of atoms, and we have to get the total charge. The total charge on this guy is 0 because there's no charge indicated, right? So we've got 5 atoms of oxygen. So we have and we have 2 atoms of nitrogen. We've got a total negative charge on this guy of -10 that we have to balance. So we know that if we call this guy X, 2 times X has to equal +10 to balance this guy. So we know that the charge, our pseudo charge that we're assigning to the nitrogen, because this is 2 nonmetals making a covalent bond, our oxidation number for nitrogen is +5. Each of those nitrogens has a +5 oxidation number. So let's do this one here. Let's do CH2O. So we know oxygen is the most electronegative. It's got to get the -2 charge. Hydrogen is going to take the +1. And we can see, and then our carbon has to fill in where everybody else left off. So we need the number of, so this is our charge. We don't know what carbon is. Carbon can be variable. So carbon is X in this case. And then we need number of atoms. So we've got 1 of our oxygen, 2 of the hydrogen, and we've got 1 of the carbon. So when we do our total charge up here, we've got a -2 from that oxygen. We've got +2 from the hydrogens. And carbon, oh, we see here, we're already balanced. We're at 0. So the charge on that carbon right now is 0. It doesn't carry any charge at all in that molecule. So we would assign this an oxidation number of 0. So 0 is a fine number to assign as an oxidation number. All right, let's look at this case where we actually have an anion present. So let's do the SO3 over here since our page was getting crowded. So this is a good one to do because we have that extra charge up there. It's not neutral anymore. So that changes our equation just a little bit. Right? So now we're still going to draw our charge box just like we have for our ionic compounds. We're going to have charge, we're going to have number of atoms, and then we'll have the total up here. So we know we've got oxygen's charge -2. There's 3 of these guys. And we don't know what our sulfur is going to be, but we know that there's only going to be 1 of those guys. So we've got a total negative charge of -6, and we've got a positive charge over here, which is going to be 1 times X. Is going to be our positive charge. And that's going to have to equal, instead of being 0, we have a -2 charge as our total, right? Because this is an anion and it's carrying extra electrons with it. So instead of equaling 0 like our other compounds normally do, this one has the charge indicated. So we would say 1x minus 6 equals -2. And then we solve for our x. X is going to equal, we bring our 6 to the other side, becomes positive 6 minus 2, or x equals 4. And so that's on the positive side. So in this case, our oxidation number for the sulfur has to equal +4, and this one -2. So those are some examples of calculating our oxidation numbers. So if your overall molecule is charged, you have to set your total charge to that charged state. Normally for most molecules it's going to be 0, but if you see you just have an ion present, then the charge on that ion has to be taken into account as the total on the molecule.